So this talk is going to be about developer tools, and in particular, it's going to be about Bloop. So Bloop is a developer tool we've been working on for the past 3 or 4 months at the Scala Center. This is the logo. It's a killer whale, and I think it illustrates very well our kind of motivation or the reason why we created Bloop. Killer whales are one of the fastest animals in the sea, and they even kill sharks, which is kind of cool. So it was an inspiration for Bloop. And before we go into details, we're going to introduce ourselves. So I'm Jorge, and I am a DevTools engineer at the Scala Center for the past 2.5 years. I co-maintain Scala's incremental compiler, whose name is Sync. I work mainly on build tools and build servers, and I also do some work on Scala C, the Scala 2 compiler, compiler plugins and infrastructure. Probably like macros and all this kind of stuff. I have to say, one of my obsessions is developer productivity. So that kind of like tells a lot about this project.
Hi everyone, my name is Martin. I am also a software engineer at the Scala Center. I've been there for a bit more than a year now. I usually work on compilers and build tools. And one of the things that bother me is when my tools get in my way and they don't let me work the way I would like to. Previously I've been working on SBT, Zing, also Scala Native, and I just recently joined the .NET team at TPFL. This is a quote that we got from a happy Bloop user. He came back on our GitHub channel and told us what we did with Bloop. They had an application that had many layers, where they had base libraries that they would build upon many layers, so that in the end they had a plugin system that they would deliver to the clients. Whenever they were editing the base of their tooling, they had to publish locally all the changes and so forth, many times, many layers, and it would take a lot of time for them. So using Bloop, they were able to simulate source dependencies, and with that, they got turnarounds in the order of seconds instead of 10+ minutes that they had at the beginning. So it's great now that we have been raising milestones for a few months, that we get more and more feedback about how people are using Bloop to develop new tools and how they are able to get new ideas of how to get more productive with our tooling in Scala. So when we see that, we think that good tools are tools that should be sufficiently flexible so that you can they can embrace your workflow and they don't get in your way. You feel empowered by them because they let you do exactly what you want, and you don't get forced into the way of working how they would like you to.
So in this talk, we're going to dive into detail about how Bloop makes you more productive. And well, of course, in order to claim that, I need to define what productivity is. So the main focus of Bloop here is that we want you to well, I'm going to define first productivity, actually. So we define productivity as you being bounded by your thinking process and not the tools you use. So you are productive if you are, stopped at some point and you need to think about the API design, and you need to think or wait until the build tool has finished compilation. So our goal here is to minimize the amount of time it passes between a code change and its result. That result may be a test execution result or end of compilation. So I imagine that most of the people that don't work on build tools see build tools like this, right? Like this beast that have many different properties. They are very different from each other, and they kind of allow you to do things in completely different workflows. So you have Pants and Bazel that are source-based dependencies build tools, and then you have Gradle, Maven, and SBT, which kind of like predicate more on binary dependencies and have other ways of working. So what's common about all of these build tools is that they all compile your code. And when we talk about compilation, well, in order to compile, you need to use the Scala compiler. But compilation is one of these services that requires or has concrete properties that are essential to the experience of the language. So in this case, what we wanted to do with Bloop is to kind of get the core of all these build tools, the core that compiles your code, and strip it away, put it in another tool, and expose it. And by definition, all these build tools would be able to reuse that core and would spend their time, or the developers working on these tools would spend their time more on the front-end part, on how people and users interact with the build tools, rather than the internals of how you get the Scala compiler working correctly. So we tried hard, really hard, and the best we could do is this. So this is how I would kind of imagine Bloop. The killer whale was the official logo. This is an unofficial logo. Heather is not around here, so it's good that I show it to you. And what we wanted basically is just to have a fast tool, a very lightweight tool as well, and a happy tool, something that you can use and be happy about it. So I would define Bloop as a Zinc++. It's, for those that don't know, Zinc is the Scala's incremental compiler. So what it does is that given a code change, you change a file in your file system, it will compile only the necessary parts of your project so that the compilation is correct. And this is basically an optimization. It's some kind of workaround for the fact that batch compilation in Scala, compiling everything all together, is a slow process. So when we think about what the tools we have right now to kind of like build upon, we have in one part of the spectrum we have a Scala C, which is the raw compiler. Has the compiler APIs, you interact with them, and then you grab the compiler to do whatever you want. You also have a CLI, but the CLI doesn't give you hot compilers, which we'll explain later what those are, and it doesn't give you incrementality either, so it's not very useful. And I think that one of the bad things about using Scala C directly is also that you cannot reuse the context in which the compiler is used. So usually compilation happens in a context, and it may be very useful for that compiler to know what that context is, so that it can apply optimizations. So right now, there is no way to do that, and we think that Bloop can be a good solution for that. In the other side of the spectrum, we have build tools. The problem with build tools is that they are focused on the user, and they are too heavyweight. They are difficult to integrate with because the users are supposed to use them, and they are supposed to be used by users and not by tools. So there's a gap to fill in here, and this is exactly what Bloop does. So Bloop gets Zinc, which is a library, and all the build tools that we've seen before grabs that library, and it gets the Zinc library, puts it in a Nailgun server, and exposes to you. And we'll see a little bit more about the properties of this Nailgun server afterwards. One important thing here to understand is that Zinc, like Bloop, doesn't aim at replacing your build tool. It rather complements it. And when we talk about build tools, they do lots of stuff, but they do also some stuff that they are not meant to do, or they are not optimized to do. So developer workflows, basically the workflows or the kind of projects we work on are very defined depending on the culture of our company, and they are orthogonal to build tools. And sometimes they require special cases. They require custom solutions so that we can make a change and make it as fast as possible. So this is one of the reasons why Bloop is important, because Bloop allows you to do this kind of stuff without making complicated changes or complicated extensions to build tools that you need to learn how to integrate with. So what can we do? What are the solutions? So the only solution that we saw 4 months ago was centralization. So we want to expose compilation as a service, and we want a server to compile them all the programs. The changes to this code base will have the most impact, because if this code base or if this service is reused by all the other build tools, then it means that if we optimize the performance of that compilation server, or if we fix a bug, that will be immediately the change will propagate immediately to the rest of the build tools that use the server, and you could upgrade the server independently of the build tool version. This is not some kind of pipe dream. There are lots of cases, lots of examples in our community in which we are not doing it right. And one example is Gradle. Gradle is an important build tool. Many companies use Scala with Gradle because they also have Java code or Kotlin code, right? And Gradle, the latest version, still uses Zinc 013, which is a compiler that was used, that was released 3 years ago. So of course that compiler is less than ideal. It's not fast and it doesn't have the best incrementality. So we want to change that.
And that's how we got the new compilation server ID that we want to push around, which is what we call the new kid in the block now. This is the old architecture that we had, where you had your IDE using one compiler with some glue code to talk to it, other CLI tools that you would use. So this is the old architecture that we had. First you have the IDE that has some glue code to talk to one compiler, other CLI tools that you would use, they also talk to one compiler, and your build tool is also using with some glue code one instance of the compiler. This has some issues. First, we have 3 different implementations of how to talk to a compiler. Also, we have 3 different instances of the compiler running at the same time, which is not very efficient. And we believe that we can do much better with this new architecture that we're proposing, in which all the different tools that you use that need a compiler are talking to the same instance of bloop. This has several advantages. First, we have only one implementation of the glue code that lets you use a compiler from the outside, and also it means that we have just one instance of bloop running at the same time on your machine. This compilation server that we want, it has to have several properties. First, it's important that it works today with Scala 2, but we also have to support the future, be future-proof and support Scala 3 today. Also, it's very important to be platform agnostic. You cannot ignore Scala.js nor Scala native, and of course Scala on the JVM is still the most important one at the moment. And whatever you have, you want to be able to use it with all the build tools. You cannot just focus on one. You have to support DBT, Maven, Gradle, whatever, and it has to be simple to integrate with this compilation server. Having this compilation server also, it allows us to do new and better optimization. We have a build graph that is statically known, which allows us to perform more optimization. We know when we can store things in memory, and when we have to store them on disk. We know when to invalidate. We don't have to perform all the work that you would have to do in a different context. We can skip class-pass hashing. We can reuse the hashes of the sources. And given the static graph that we have, we can also do a better work at parallelizing all the tasks that you get to the compilation server. So I was talking before about having only one instance of the compiler running on your machine. But why is it important? That's because you get hot compilers. A hot compiler, as you probably know, is a compiler that has been heated up by the JVM, which while executing your code, it's optimizing it so that it performs much faster. Having a hot compiler is really useful because it's going to compile much faster, and if you discard it, it's going to be a huge problem for your productivity. And you may not know it, but getting hot compilers is happening really, really often, for instance, with SBT. Whenever you try to reload, it's going to discard all the hot compilers that you had. If you, for instance, exit your build tool using Ctrl+C, it's going to discard all the hot compilers that it had. Or if you have 2 different instances of SBT running concurrently in separate projects, nothing is shared between the 2, and you don't benefit from the hot compilers that you had for one project in the other. There are some benchmarks for comparing the performance of hot versus cold compilers that in Grafana, that's a project from the Scala compiler team. And it shows that it can be up to 18 times slower to compile with a cold compiler versus a hot compiler. Also, another reason why you don't want to discard hot compilers is because it takes a lot of time to get the compiler hot enough. It consumes CPU cycles, it takes your battery, consumes RAMs. So it's really too bad to do again and again and again the same work where you could just keep the hot compiler and be fast all the time. So now we want to show you a bit how does bloop look like. It's a command line tool first, which is made so that you get the snappiest workflow that you could get. We don't want to get in your way. You can use the shell that you're used to, the shell that you love and you've configured to better suit your workflow. what is nice also is that we've worked very hard to get nice tab completion. Everything is contextual, so that, for instance, you get here the completion for the main method that are defined in your project. And yeah, without having to compile everything. Looking great. We have, this is what the configuration for bloop looks like. This is something that will be generated by your build tool for you. And we've made it so that it's pretty transparent and very well specified. You can see, for instance, it knows what is the base directory of the project, where to find the sources. You have the full class path that that will be passed to the compiler. Yeah, basically everything that you would need to perform incremental compilation, running your project, finding the tests, and so on and so forth. The transparency that you get with this configuration file is also helpful, because it's going to let you figure out really easily by looking at the configuration file why something may have gone wrong, why you don't find a test, why you have class not found exceptions, and so forth. You could also use this build tool, given that it's this configuration file, given that it's so well specified, to create new tools. That's exactly what they've done in the example that we've shown at the very beginning when they simulated source dependencies using bloop. There are lots of tools in the command line or whatever to parse JSON and to be able to interact with it, and that makes it very easy to write new performant tools using bloop. This is a link to the specification of the configuration format if you're interested. So now about configuring bloop. It's important to understand it's a two-step process. First, you will need you'll use your existing build tool and build definition to generate all the configuration for bloop, and then you get ready with using bloop. This is as simple as it gets to install bloop and to get ready to work. First, you add the SBT plugin that is going to add some comments to SBT so that it can export the configuration of your build to the configuration format that bloop understands. And then the second part is to do SBT bloop install, which will actually generate all the configuration files. Bloop defines 4 main comments. The first one is bloop compile, which obviously compiles your project, its dependencies, and everything is done as much in parallel as possible. It supports file watching, so that you can pass it --watch, and it will recompile whenever you change the source files. You can use different compilation reporter to get error messages that you like best. And there are many more options that you can use. Everything is very well documented. For all the comments that we have, you can use the help flag so that it shows you everything and explains to you how it's going to affect how the compilation is going to be performed. The second command is bloop test, which run the test for a project and its dependencies. You can, if you want, just pass it isolated so that you test only one project, and you can use only to filter the test so that you run just a given test suite or maybe some tests inside suite. It also supports file watching so that you can rerun your test whenever you save a file. Also, we have bloop run, which will run the main classes of the project. Also, it supports watch. Nice example here is that you can use your shell and the shell expansion to, for instance, find all the images to train the neural network on, write the data to some variable that is expanded by your shell for you. And you get all of that for free, whereas, for instance, with SBT, you would have to write a separate task to get all the files, and then you would have to find some way of getting the home directory expanded and so on. Here, you can simply use the shell that you know to get that for free. And the last command that you interact with the most is bloop console, which is the equivalent of SBT console. It opens a REPL with your project and its dependencies on the class path so that you can quickly try things out. All the comments that we have support tab completion. You can discover things very easily. It's completely contextual. So if you have to complete test names, it's going to do it for you. If you need the name of main class, it's going to find it for you. And you have access to all those features from your real shell. I want just to very quickly demo how you can set up bloop to work, for instance, with utest. So it's really as simple as going to plugins.sbt. You had the SBT plugin for bloop. I'm using M10 that we released just a few days ago, and you do bloop install. So as you can see, generated all the configuration file for bloop. We have, in this case, this is a project that defines JVM, JS, and native interrupt. So there is one configuration for each of them, and for each project we generate two configurations, the compile configuration and also the test configuration. So now let's see what happens with bloop. So first, I'm running bloop M10, which is the most recent version that we have, and let's see what happens if I compile. Sorry, I get the tab completion to get the name of the project. Oh, I need to clean first. Here it's compiling everything in parallel. And here we go. So now what happens if I maybe try file watching? Let's try to modify something. Here it's finding again the differences pretty fast. So we also support test, of course. Let's run JVM because we don't have support for running on the other platforms at the moment. And again, it's pretty fast. All the tests are running. So as you can see, it's very simple to get bloop ready. It's just adding one line to plugins.svt.
Well, these tasks are nothing new under the sun, right? I mean, every build tool supports them. So what's the deal about? I mean, what's the hype about? So the hype is about integrations, and I can see already your faces like screaming and saying, "Oh no, a new tool, right? I don't want to learn a new tool." And the fact that bloop is a CLI gives you some advantages over having a shell, for instance, as in SVT, but it's not worth the creation of a new tool. So our focus has been on making integrations better. And this is the thing we've been working on during the past weeks. And this is something that we are going to show now, and we're going to explain how we've achieved that and how we are achieving it, because it's like a process that is still under work. So the first realization, the first kind of key thought is that we want bloop to be used by all the tools in our ecosystem. We don't want to leave any tool outside of it. So in the previous case, I mentioned Gradle. So now that we have the opportunity to create something new, we want the Gradle users to benefit from the very latest compiler technology that we have in Scala and the best Scala language experience possible. And we want it to have same experience as you have in SBT, which is the kind of official Scala build tool, or as you have in Maven or Pants or whatever build tool you use. So then it's clear that improving SBT only is not a solution, and improving new build tools like Mill or Fury or investing resources in our next favorite build tool is not going to be the solution either. There is a lot of people out there that won't migrate builds because migrating builds takes a lot of time, takes a lot of expertise, and it's not an easy process. So one of the most important projects we've been working at the center for the past months is the build server protocol. So the build server protocol is our solution to integrations, and integrations with build tools in particular. So you have different clients, and the clients connect to servers. In this case, bloop can act as a BSP server because it has all information about your project and can provide all this information to the clients. But then, what are the clients? So the clients are language servers and editors. So in this case, IntelliJ has its own language server for Scala. It gives you completions. It gives you an IDE experience, right? So that's what we call a language server. So IntelliJ could integrate with bloop via BSP or with whatever build tool there is that implements the protocol. And as you see, this is a very similar protocol as LSP. It's trying to solve the same problem, but instead of applying it to languages, we are applying it to build tools. if you want to know more about this, because this is a very lengthy kind of topic to discuss about, I recommend you to check out this talk I gave at the Scala Sphere 1 month ago with Justin from the IntelliJ team, in which we show the latest advancements in the BSP implementations, and we're gonna show a little bit today, but we are just gonna go briefly through a process or through the use cases and show why this is useful for Bloop. It is important to notice as well that BSP is completely independent to Bloop, and it happens to be implemented in Bloop first because it makes a very good testbed for testing whether BSP is a solution or not. We're still at the process of experimenting, and it also makes it a very nice case because we can abstract over build tools. I'll dive a little bit deeper into that afterwards. So the most important use case that BSP supports is an efficient import project. So probably some of you have imported with IntelliJ your project, and it's taken a lot of time, maybe in the order of seconds, 4 minutes to import Apache Spark, 10, 20. I've seen 20, by the way. So this is a very inefficient process, and it kills productivity. Every time this happens to me, and every time I feel like I need to update the indices in IntelliJ, it really breaks my heart. So BSP tries to fix this problem by making it snappier and making it better. So the idea is that instead of exporting all the information about the build to the IDE connects to the source of information, to the build tools, and asks the build tools what you have in the workspace, what projects you have, what are the class paths, what are their names. And in our case, we can use the same trick that you would use for a BSP server, but instead have all these build tools that would be also BSP servers be BSP clients. So I know that some of you have custom solutions. For instance, those that develop HTTP servers need to be in the SBT shell and need to have the Play integration working there. So of course, using a CLI application to compile your code is not a solution. You need to integrate everything. You need to make the use of Bloop transparent to the user. And that's what this enables us to do. So in this case, Bloop would be the server, and SBT would be the client. So when you type compile in your project, what SBT would do under the hood, or what Maven would do under the hood, is send a compile request to the Bloop server. And there, we would compile your code in the fastest way possible and get it back to you. So these are pictures of something that we've been working on with. We've been working with the JetBrains team. So this is a screenshot of IntelliJ, and it's a screenshot of IntelliJ showing a compilation error that comes from Bloop. So Bloop imports your Bloop has the project definitions of all your build, right? And all IntelliJ does is that you import a project, but instead of selecting SBT, you select BSP. So the BSP implementation right now in IntelliJ would get all the data of your build, import it, and then would allow you to compile from the UI. So in this case, we get diagnostics in the editor. You don't get it in a shell. You get it directly in the editor, and that makes a very nice experience when you are developing code, and makes it snappy as well. A good case as well is that instead of having a file watcher that listens for changes in your source files, IntelliJ can tell directly to the server which files change, and that makes for also a faster compilation.
Something that we've not really talked about yet is benchmarking the compilation and how fast can Bloop actually compile. So we've been improving on the compilation Scala C benchmarks project from the Scala compiler team at Lightbend, in which they compare the performance of Scala C versus also the performance of Scala C with SBT. And we've been improving on that to also compare with Bloop. So first, we've been trying with a smallish to medium project, maybe. It's SBT. It's the Scala ecosystem build tool. I guess everybody knows it. It has about 800 source files, 50,000 lines of code, and we've seen that comparing with Bloop, we get about 25% faster. We've been trying with something that's quite a bit larger already, 1,800 source files, 100,000 lines of code, and here too we get 28% faster when combining the Guardian frontend. Next was Akka, which is even a bit bigger, 330,000 lines of code, 1,800 source files, and we get here to 19% faster when compiling. Apache Spark is the biggest that we've tried. It's 400,000 lines of code, and here too we get 28% faster. I should mention also, this is the compilation of hot SBT versus hot bloop. So we've been running for 10 to 15 iterations so that we get the hot compilation state. We're making sure it's stable because the machine have been stabilized. We're using JImage to make sure that everything is reproducible as much as we can. And those are the numbers that we get if we plot everything normalized. So in green, this is bloop versus SBT in blue. Oh, we should have switched that. So as you can see, even if the project is small to big, you can expect to get with Bloop at least 20% improvement, which I think is nice when you compare that to all the work that has been done on the Scala C compiler to get a similar performance improvement you're going to do today using Bloop instead of SBT.
So, of course, the most interesting thing of Bloop to me is the new use cases that it enables and how we can invest our resources at the Scala Center in an effective way and have the biggest impact out there for you guys so that you can develop Scala code better. So one of these use cases is remote compilation. The idea of, okay, so I reuse hot compilers locally, but I want to reuse them in the cloud as well because I want to compile as fast as possible. And that's especially important for CI turnarounds. That it's especially important that CI turnarounds are as fast as possible because that encourages changes and you want to be blocked by your CI to report errors back to you. So it is a popular use case for CI servers. There are some builders that are tackling this problem. It's not an easy problem. For instance, Bazel is has now a remote compilation API. But it requires, as I said, architectural changes, and those are not easy to do even for one build tool. I'm not going to dive into the details now about what's required for this feature, but it's an important feature to consider in the future. There is something special. Well, there is a use case, and that is the use case of traditional compilation that it could be improved even if we don't realize. And usually when we have 4 modules, like let's say A, B, C, and D, and B, C depend on A, and D depends on C, you need to finish until the compilation of A is done. You need to wait until the compilation of A is done so that you can start compilation of B and C, and you need to do the same for D. So D needs to wait for C to finish so that you can start a compilation there. But this is less than ideal, and there are some changes in the compiler that we can make to prevent this, like to change a little bit this picture and give you better performance in both batch compilation and incremental compilation. And that is called pipeline compilation. So pipeline compilation is the idea of, okay, it happens that I can start compilation of dependent modules way before the compiler has finished. And the reason for that is that the first part of the compilation is used for type checking your program, and the second part is used to kind of like change your program so that the generation of class files can be done. And here we are taking advantage of the fact that we don't need the class files from A to compile B and C. And on average, that actually makes a huge difference because type checking a program takes around 60% of your time, of the time it takes to compile, and 40% goes to other phases that are related to class file generation. So by starting before the compilation of all the dependent modules, no matter what the shape of your build graph is, we can make a huge difference in your compile times because the changes accumulate. So if you have BC in this case will start 40% like before, but D will start 40% plus 40% before. So this idea was pitched in by Rory Graves last year, I think, at Scala Sphere, and I fell in love with this idea. I think it was wonderful, and I decided to implement it in Bloop. So I implemented it in Bloop, and I have the changes also required in Zinc. The nice property of this implementation is that it's compiler agnostic. And it means that we will be using pipeline compilation for both Scala 2 and Scala 3. And it means that we have a high impact for any kind of build graph you have. So you have a sequential build graph in which you have 3 modules and one depends on the other one and the other one depends on the other one. Then you'll get there a 40% faster compilation. But if you have highly parallelizable build graph, and you also have a machine with lots of cores, the impact can be huge. We don't yet have results for the kind of impact that this feature does, but we suspect that it will be important, and we will showcase the benchmark numbers in New York. So thank you for listening to us. If you have any questions, we're here and happy tooling.
So, thanks a lot. Are there questions right away? Oh, a lot of questions. I start.
I was wondering, to what level of detail does the BSP protocol go for IDEs? Can they use it to do things like find implicit conversions and highlight type signatures and stuff like that? Because otherwise they'd have to have their own cache for that sort of stuff anyways.
So BSP in this case doesn't do any of that. So BSP only provides you as a language server the information about the class path and the kind of libraries you need to index, or you need to kind of provide all the IDE information from. So BSP is only about build tools. It's only about kind of like expressing this build graph and giving it to the client, and the client can do whatever it wants. So you could imagine if you are a VI user and you don't like IDEs, you could imagine a BSP integration in VI that just allows you to compile from the user interface and directly tells the server, hey, compile this thing, and then comes back, right? So in this case, it's independent from IDEs and it's independent from LSP. It rather complements LSP, and it doesn't try to kind of replace the purpose of LSP.
In order to do say your cursor is on a val and you want to know what the type is, in order for the IDE to show that to you, it has to have the whole class path.
Of course, yeah.
So you still have a duplicate memory usage then, the IDE needing to figure that out and the build server in the background. I kind of for a moment was hoping that like all the, whatever was it, 2 gigabytes of dependencies I have on my class path now only need to be in memory once, and the IDE and...
But why do you need to have it in memory?
In order to calculate the type.
But the type is like, that's an implementation detail of the LSP server. So when we talk about language servers implement the LSP protocol, right?
Yeah.
So they are servers on their own. But in this case, when these servers need to connect to build tools to kind of know what the class path of what the projects in your workspace are, right? But it doesn't, that's an independent problem from the problem of doing type on hover or go to definition. It's independent. So you get the information you need for providing, for providing the IDE experience from the build tool. But that's a completely different problem.
I agree, but let's take it offline. It's okay.
Okay.
Yeah, so you said that you could do this for multiple projects, and they have then one instance running. But my experience is that most projects have different versions of the compiler in their requirements.
Mm-hmm.
So then you would have multiple versions of the compiler hot and running in memory.
Sure.
Yeah.
You have different class loaders for every compiler version you use. So of course you'll use a little bit more of memory, but
and you have little less gain of hot compilers.
Sure, if you use different compiler versions for every kind of build you have, yeah. But the idea is that usually I haven't seen that use case much, but in my experience, all the builds use the same compiler version. And if you don't, you are probably stuck on 2.11 and 2.12, right? So you'll have one class loader heavily optimized by the JVM for 2.11 and the other one for 2.12. But you'll get a speed up.
Just want to clarify a little bit about the integration with IDEs. So do I understand correctly that when you change SBT file, let's say, you still need to run the import bloop, or how's it called, start bloop, because bloop needs this JSON to generate a JSON file. So you essentially need to run SBT again. Kind of start SBT, go for all this ordeal of SBT loading, etc. So is there really a gain in kind of performance when you need to refresh the project?
Right. So that has to do with the way Bloop works right now as a CLI. But when we were talking about integrations, that problem goes away completely, because you don't need to create a configuration file in your disk in order to communicate with the Bloop server or Bloop BSP server. You need to you don't need the Bloop configuration files there, because you just need to send a request of compilation, or I want to see what projects you define. So in that case, that was BSP was the solution of the kind of not ideal integration we have right now with SBT, in which you need to do this two-step process.
Okay, so if like SBT will be running already kind of prepared, and then Bloop will be also running like a server, then IntelliJ will kind of be much faster to refresh the project when you change SBT
indeed.
file.
So you have like one
like
Bloop BSP server with all the information, and then you have like IntelliJ connecting to the BSP server and SBT connecting to the BSP server.
Okay, so then IntelliJ will not need SBT server running in order to refresh the project.
Yeah,
right.
You wouldn't need that.
Okay.
So, and the neat thing about that is that it works also for other build tools like Maven and Cradle and whatnot. And you only need to maintain one BSP integration, the one in IntelliJ and the one in the build tools.
Could you maybe show us a short video of the IntelliJ integration instead of just screenshots?
You already know. We don't have the time for it.
Yes, you can show it in the background.
Okay. Right.
So I think there's maybe time for one or two more questions.
You mentioned play, short, very short. How does that integration work today, or does it not work at all, or?
It doesn't work at this moment, but we're working on a better SBT integration based on the BSP client, like architecture, so that use case is supported. Yeah. At the moment, it is not.
So in the future, you will be able to run Bloop with Play framework and
Indeed,
have the whole pipeline.
The idea is to fully integrate with the build tools you use and to complement, while still giving the best performance when compiling.
So I think that were all the questions. Thank you very much.
Okay, thank you.
You managed to keep everyone awake.
We actually have here like a video that Justin just sent me now of how the import project works for Bloop. So in this case, we are showing how like Bloop is running in the background right now, and we have IntelliJ. So we say, okay, import a project with BSP, and it immediately, like in 640 milliseconds, it kind of imports all the project. So if you do it for a big project like Apache Spark, the difference is very big. So we have Apache Spark importing via BSP in 9 seconds with Bloop, and via SBT it takes around 4 minutes. So every time you reload or you change like a dependency, you need to go through all this process, and BSP makes that much better.